deep in the jungles of Central America, carved into stone temples over 1,000 years ago, are numbers that would have baffled European scholars of the same era. A shell symbol representing 0, a dot for 1, a bar for 5. With just these 3 symbols, Mayan mathematicians could write any number, no matter how large. But here's what makes this extraordinary. They invented 0 independently, without any contact with the old world civilizations that also discovered it. And they didn't just invent 0 once. They invented it twice, using it in 2 completely different ways that wouldn't be understood in Europe for centuries. While medieval Europe was still calculating with Roman numerals and treating 0 with suspicion, Mayan astronomers were using 0 to create calendars so accurate that they tracked Venus's movements to within hours over centuries. They were performing calculations involving millions, using place value notation, and understanding mathematical concepts that would seem revolutionary when they finally appeared in European mathematics. Welcome to Math's Whisperer, where we uncover the hidden stories of mathematics. I'm your host, and this is Season 2, Episode 5. Today, we're journeying into the Mayan world to discover how one of history's greatest civilizations created mathematics that was, in many ways, more advanced than what existed in Europe at the same time. The Maya civilization flourished in Mesoamerica from around 2000 BCE to the Spanish conquest in the 16th century CE. Though the classic period from 250 to 900 CE represents their mathematical and astronomical peak, they built magnificent cities like Tiku, Palenque, and Chichen Itza, created intricate writing systems, and developed sophisticated mathematics and astronomy. What makes Mayan mathematics particularly fascinating is its complete independence from Old World mathematical traditions. The Maya had no contact with Babylonian, Greek, Indian, or Chinese mathematicians. They developed their mathematical system in isolation, which means every insight, every innovation, every discovery was purely their own creation. And yet, they arrived at solutions remarkably similar to those developed independently on the other side of the world. This tells us something profound. Mathematics isn't arbitrary. Given similar problems and sufficient time, intelligent people will discover similar mathematical truths, regardless of culture or geography. Let's start with the Mayan number system, because it's beautifully simple yet remarkably powerful. The Maya used a base 20 system called vigesimal. This makes sense given human anatomy. We have 20 digits total, 10 fingers and 10 toes, just as base 10 likely emerged from finger. Counting, base 20 suggests counting on fingers and toes. 2 right numbers. The Maya used only 3 symbols. A dot represented 1, a bar represented 5, and a shell symbol represented 0. 2 right 1 through 4. You use dots. 1 dot, 2 dots, 3 dots, 4 dots. Simple dot. 2 right 5, you used a bar. 2 right 6, you put a dot above the bar. 7 was 2 dots above a bar. 8 was 3 dots above a bar. 9 was 4 dots above a bar. 2 right 10, you used bars stacked. 11 was 2 bars with a dot. 15 was 3 bars. 19 was 3 bars with 4 dots on top. Beautiful, right? You can write any number from 0 to 19 with just these combinations of dots and bars. But here's where it gets really clever. The Maya used positional notation, just like we do. But instead of each position representing a power of 10, each position represented a power of 20. In our base 10 system, reading from right to left, you have the ones place, the tens place, the hundreds place, the thousands place. Each position is 10 times the previous one. In the Mayan-based 20 system, reading from bottom to top in their vertical notation, you have the ones place, the 20s place, the 400s place, 20 times 20, the 8000s place 20 times 20 times 20, and so on. So if you saw 3 dots in the ones position and 2 bars in the 20s position, that would be 3 plus 10 times 20, which equals 203 in our notation. This system allowed the Maya to write enormous numbers using relatively simple combinations of dots, bars, and shells. They regularly worked with numbers in the millions, something that would have been incredibly cumbersome with Roman numerals. But the revolutionary element, the feature that puts Mayan mathematics among history's great achievements, is zero. The Mayan zero, represented by a shell symbol, appeared in inscriptions by at least 36 BCE, and possibly earlier. This makes it one of the earliest uses of zero in human history, contemporary with or even predating some uses in India. But the Maya understood zero in not just one but 2 sophisticated ways. First, they used zero as a placeholder, just like we do. In our system, the number 205 uses zero to indicate that there's nothing in the tens position. Without that zero, we couldn't distinguish between 25 and 205. The Maya used their shell symbol the same way. If you had nothing in a particular position, you placed the shell there to show the empty position. This placeholder zero is essential for place value notation to work. Without it, your number system becomes ambiguous and difficult to use for calculation. But the Maya also understood zero as a number in its own right, a quantity representing nothing. This is a deeper, more abstract understanding. Zero isn't just marking an empty position, it's a number you can work with, add, subtract, and use in calculations. This dual understanding of zero as placeholder and as number represents sophistication, mathematical thinking. It took European mathematicians until the 12th century to fully accept zero. And even then, some resisted it as dangerous or heretical. The Maya were using zero routinely over 1,000 years earlier. They needed zero for their most important application of mathematics, creating and maintaining calendars. The Maya were obsessed with time. They tracked multiple simultaneous calendars with different cycle lengths. Understanding Mayan calendar systems requires understanding their sophisticated use of numbers and zero. The Haab was a 365-day solar calendar with 18 months of 20 days each, plus 5 extra days considered unlucky. This gave them 360 plus 5, 365 days. Remarkably close to the true solar year. The Tzolkin was a 260-day ritual calendar combining 20-day names with 13 numbers. Every day had a unique name-number combination that repeated every 260 days. These 2 calendars ran simultaneously, like interlocking gears. A specific combination of Haab date and Tzolkin date would repeat every 52 years, a period called the calendar round, but the Maya wanted to track longer time periods. They developed a long count calendar, which counted days from a mythological starting point, August 11th, 3114 BCE. In our calendar, the long count used modified base 20 notation. The first position counted days kin. The second counted groups of 20 days called numerals. But here's where it gets interesting. The third position didn't count. Groups of 400 days 2020 as pure base 20 would suggest. Instead, it counted tons, groups of 360 days, approximating the solar year. Why this modification? because the Maya wanted their long count to mesh with their 365-day solar calendar. This shows mathematical flexibility. They understood pure base 20, but modified it when practical needs required. Above the ton were Catton's 20 tons equals 7,200 days. Bacton's 20 Cattons equals 144,000 days, and even longer periods. A long count date might look like 9.12.2.0.16, meaning 9 Bactons, 12 Cattons, 2 tons, 0 uinals, and 16 kins since the starting date. Try expressing that in Roman numerals. Try even imagining it. The Mayan system made it straightforward. This calendar system required constant astronomical observation and complex calculations. The Maya tracked Venus with extraordinary precision. They knew Venus's synodic period, the time it takes to return to the same position, relative to Earth and Sun, was approximately 584 days. Their calculations were accurate too, within hours over centuries of observation. They predicted eclipses. They tracked Mars, Mercury, and other planets. They understood lunar cycles precisely enough to create eclipse tables, predicting when eclipses would occur. All of this required mathematics. Addition and subtraction, certainly, but also understanding of cycles, periods, and synchronization. They needed to calculate when different calendar cycles would align, when celestial events would occur, when rituals should be performed. Imagine being a Mayan astronomer. You're responsible for maintaining the calendar, predicting eclipses, determining auspicious days for planting or warfare. You work at night, tracking stars and planets across the sky. You record observations in codices, bark paper books with hieroglyphic writing. You perform calculations using your base 20 number system, using 0 to mark empty positions and 2 represent the starting points of cycles. You're doing mathematics at a level of sophistication that matches or exceeds what's happening anywhere in the world at that time. And you're doing it completely independently, with no knowledge of Babylonian astronomy, Greek geometry, or Indian algebra. The Dresden Codex, one of only 4 surviving Mayan books. The Spanish destroyed hundreds during the conquest, contains astronomical tables of stunning accuracy. Pages of Venus tables predict the planet's appearances and disappearances. Lunar tables track eclipse possibilities. Solar tables coordinate the 365-day year with longer cycles. These tables required thousands of calculations. The Maya developed methods for adding and subtracting large numbers in their base 20 system. They understood remainders and divisibility. They worked with common multiples and synchronized cycles. One remarkable achievement is the calendar-round correlation. The Haab has 365 days. The Tzolkin has 260 days. When does a specific Haab-Tzolkin combination repeat? This requires finding the least common multiple of 2060 and 365. The Maya understood this problem and knew the answer: 18,980 days, or 52 years. This is the least common multiple of 260 and 365. They didn't have our algebraic notation. Understood the concept and used it to structure their calendar system. They also understood sophisticated concepts about planetary motion. Venus appears as morning star, disappears, reappears as evening star, disappears again, in a 584-day cycle. But this cycle doesn't sync perfectly with the 365-day solar year, or the 260-day Tzolkin. The Maya calculated that 65 Venus cycles equal 146 Tzolkin cycles equal exactly 104 solar years. This synchronization point required precise calculation and long-term observation. Think about the mathematical thinking required. You're tracking 3 different cycles with different lengths. You need to find when they all align. This is essentially solving a system of modular equations finding common periods among different cycle lengths. The Maya didn't write equations as we do, but they solved the same mathematical problems. Mayan mathematics also appears in there. Architecture and engineering. The pyramids at Tikal, Chichen Itza, and other sites weren't just religious monuments. They were astronomical observatories with specific alignments. The pyramid of Tzolkin at Chichen Itza has 91 steps on each of its 4 sides, plus 1 platform step at the top, totaling 365, matching the solar year. During equinoxes, sunlight creates a serpent-like shadow descending the pyramid's side. This required precise mathematical calculation of angles, proportions, and astronomical alignments. Buildings were oriented to mark solstices, equinoxes, and Venus's extreme positions. Windows and doorways were positioned to frame specific celestial events. This required trigonometry, though not in the formal way later developed by Greek and Islamic mathematicians. The Maya understood angles, ratios, and spatial relationships well enough to encode astronomical knowledge in stone. They also used sophisticated surveying techniques. Mayan cities were built in challenging jungle terrain, yet buildings are precisely aligned over large distances. They created straight causeways, called sakbib, connecting different parts of cities, sometimes stretching kilometers through dense forest. This required accurate measurement and calculation. Now let's address what's often asked. How far did Mayan mathematics develop? Did they have algebra, calculus, or higher mathematics? We honestly don't know the full extent because so much was destroyed. Spanish conquistadors and missionaries, viewing Mayan books as pagan heresy, burned thousands of codices. Bishop Diego Jalanda, in a single auto da fe, in 1562, destroyed the accumulated written knowledge of an entire civilization. Only 4 codices survived to the present day. Imagine if 4 books were the only surviving written legacy of Greek mathematics, or Chinese mathematics, or any other tradition. How much would we miss? How skewed would our understanding be? What we know suggests the Maya had sophisticated computational abilities and deep understanding of cycles, periods, and astronomical patterns. Their mathematics was highly developed. For astronomy and calendrics, whether they pursued pure mathematics for its own sake, developed abstract algebra, or explored other mathematical domains, we simply don't know, because the evidence was burned. But what survives is impressive enough. The Dresden Codex alone proves mathematical sophistication that rivals anything in the Old World at the same time, period. Let's talk about what makes Mayan mathematical achievements particularly significant. First, independent invention. The Maya developed zero, place value notation, and sophisticated astronomical mathematics without any contact with Old World civilizations. This wasn't borrowed or transmitted, it was created from scratch. This demonstrates that advanced mathematical thinking emerges naturally when intelligent people tackle complex problems. Second, practical application. Mayan mathematics wasn't purely theoretical. It served religious, agricultural, and administrative needs. They needed accurate calendars for planting crops, timing rituals, and coordinating their civilization's activities. Mathematics emerged from necessity but became sophisticated in the pursuit of precision. Third, integration with other knowledge. Mayan mathematics was inseparable from their astronomy, architecture, religion, and writing. It wasn't isolated in ivory towers, but woven into the fabric of their society. This holistic approach to knowledge has lessons for modern education. Fourth, the base 20 system. While we use base 1 and Babylonians used base 60, base 20 is equally valid and in some ways more intuitive, matching all fingers and pinging toes. This reminds us that our mathematical conventions aren't the only possible ones. Different systems can work equally well. Fifth, the dual zero. By understanding zero both as placeholder and as number, the Maya achieved a sophisticated abstraction that European mathematics struggled to accept for centuries. This shows that mathematical sophistication isn't limited by technology or writing systems, it's about conceptual clarity. The story of Mayan mathematics also carries tragic lessons about the fragility of knowledge and the consequences of cultural destruction. When Spanish conquistadors arrived in the 16th century, they encountered a civilization with writing, astronomy, mathematics, and sophisticated urban planning. Some Spaniards recognized this sophistication, but religious fervor led to systematic destruction of Mayan cultural heritage. Books were burned as idolatrous, scholars were killed, knowledge systems were suppressed. Within a few generations, much of classical Mayan mathematics and astronomy was lost, surviving only in stone inscriptions and the 4 codices that escaped destruction. We're still deciphering Mayan hieroglyphs, still understanding their mathematical notation, still discovering what they knew. Modern archaeoastronomers use computers to verify Mayan astronomical observations and have found them remarkably accurate. Epigraphers are still translating inscriptions that reveal new mathematical insights. What could we have learned if the codices had survived? What mathematical techniques did the Maya develop that we'll never know about? This is Alexandria burning all over again, destroyed by those who feared or dismissed it. The lesson is urgent. Cultural destruction means intellectual destruction. When we erase a civilization's books, we erase their accumulated knowledge, their insights, their contributions to human understanding. Modern scholars, including many of Mayan descent, are working to recover and preserve what remains. The decipherment of Mayan hieroglyphs, largely accomplished in the late 20th century, opened new windows into Mayan thought. Archaeological discoveries continue revealing new inscriptions. Mathematical analysis of surviving codices shows ever more sophistication. We're learning that Mayan mathematics was more advanced than previously thought. Each new translation, each new analysis, raises our estimation of their achievements. Today, Mayan mathematical heritage deserves recognition. Alongside Greek geometry, Chinese algebra, and Indian arithmetic, the independent invention of zero, the sophisticated calendar systems, the astronomical precision, these are among humanity's great intellectual achievements, and for students learning mathematics, the Mayan example teaches valuable lessons. Mathematics isn't owned by any culture. It emerges wherever humans think deeply about patterns, numbers, and relationships. The symbols may differ, the notation may vary, but the underlying truths are universal. Base 20 is as valid as base 10. A shell is as good a symbol for zero as a circle. Vertical place value notation works as well as horizontal. The Mayan system teaches us that mathematical diversity enriches rather than diminishes mathematics. So next time you write a zero, remember you're using a concept that the Maya understood over 2,000 years ago. When you think about place value notation, remember that Mayan astronomers used it to track Venus's motion across centuries. When you marvel at ancient achievements, remember that some of the greatest weren't in the Mediterranean, but in the jungles of Central America. The Maya created mathematics worthy of any civilization in history. And they did it twice, inventing mathematical concepts independently that others also discovered, proving that mathematical truth transcends culture and emerges wherever humans seek understanding. If you're fascinated by how different civilizations independently developed sophisticated mathematics, subscribe to Maths Whisperer. We're releasing daily episodes exploring mathematical thinking across cultures and time periods. Tomorrow, we're traveling to ancient India to discover how Indian mathematicians gave us the decimal system, developed algebra centuries before Europe, and created mathematical techniques that changed the world. Hit subscribe, ring that bell, and comment. What other Mayan achievements would you like to learn about? Let's keep exploring mathematics together, one whisper at a time.